Hello, everyone. Welcome you back to study MA22, which is a course about the measurement and the sensing system. Today, we move on to study the lecture on measurement of temperature. As usual, before we enter the study of today's lecture, let me give you a quick overview or review about the answer to these 4 common questions that you may have in mind. Question number 1, why to study this course? Question number 2, how to study this course? Question number 3, what are you going to learn from this course? Question number 4, how are you going to learn the knowledge from this course, right? So let me begin with the overview about the answer to question number 1, which is why to study this course. By now, you should know that our mission on Earth includes number 1, to understand the world, and then number 2, to improve or to change the world. Then how to understand the world? The answer is to discover knowledge about the physical world. Then how to discover knowledge? The answer is to have sensory data. Then how to obtain sensory data? The answer is to make use of measurement and the sensing system. All right. Then for our second mission, which is to improve or change the world, then how to improve or change the world? The answer is to invent smart products, smart system, and smart machine. Then how to invent these system, this product, and this machine? The answer is to incorporate feedback control group inside the design of a smart system, smart product, and smart machine. All right. Then what is a closed loop control system? The answer is closed loop control system is a system with 3 basic building blocks or basic building module. One of them is the sensor or measurement and the sensing system. All right. So therefore, it is very important for you to study this course. For example, this slide showing you the presence of a smart parking system in the future city, smart light system or smart street lighting system in future smart city, and also the presence of a smart building system, smart home system, smart environmental system, smart healthcare system in future smart city, all right? And also you see the possible deployment of the Internet of Things in future city, okay? And inside the Internet of Things, there is one important device, which is a sensor, right? Or measurement and the sensing system. Okay, so that gives you the answer about the motivation behind the study of this course. All right. Then the second question that you may have in mind is about how to study this course. My advice to you is to put yourself into the mindset of a designer. Then with the keyword of a design or designer, automatically you will raise these 4 questions. Question number 1, who are the user? Question number 2, what are the needs from this user? Question number 3, what should be the functionality of the future product or future system that you are going to develop in order to meet the need of this user? Then question number 4, what should be the solution behind the design of your future product or future system, right? So the answer to question number 1 should be obvious, okay? The user include human being as well as smart product, smart machine, and the smart system. Then what are the needs from this user? Their needs are the same. It is to have sensory data, all right? Then what should be the functionality of your product or your system, such as a sensor, Internet of Sensor, or networking of sensor, okay? Which will meet the need of this user. So answer depends on the specific nature of the user, right? For example, a vehicle may need a certain type of sensor. A robot may need another set of sensor, all right? So their need may not be exactly the same. So therefore, the answer to question number 3 depends on the specific nature of user, all right? Then what should be the answer to question number 4? The answer is to study well this course. At the end of the study of this course, you will know the answer to question number 4, right? Then the third common question that you may have in mind is about what are you going to learn from this course? Basically, this course covers the study of physical principle behind the design of popular sensor in electric domain, in mechanic domain, in environmental system, and in intelligence system, right? And in addition, this course covers basic detail about the physical world, the basic detail about the conceptual world, and also this course gives you the basic knowledge for you to cope with randomness in the physical world and for you to understand fuzziness in the conceptual world. All right. Then question number 4 that you may have in mind is about how to apply learned knowledge from this course. So the answer is to apply the learned knowledge like to guide the design of your future sensor or future measurement and the sensing system, right? The general guideline is to follow these 2 steps in your design. Step number 1 is to transform the value of a physical quantity on the measurement into readable value. Step number 2 is to calibrate your measurement and the sensing system so that the output from your measurement and the sensing system is exactly equal to the value of physical quantity on the measurement. In addition, the unit of a measurement assigned to the output is exactly equal to the unit of a measurement of the physical quantity on the measurement as the input, right? Then for the implementation of step 1, you may face 2 situations. The first situation corresponds to the case in which it is good enough for you to make use of a single front-end sensing element in order to transform the value of a physical quantity on the measurement into readable value. But in most cases, you may encounter the second situation in which you have to make use of both front-end sensing element and the back-end sensing element in order to transform the value of a physical quantity on the measurement into readable value, right? So you follow this guideline, then you should be able to apply learned knowledge, okay, in order to come out the detail of the design of your future sensor or future measurement and the sensing system, right? Now we are ready to enter the study of today's lecture. So today's lecture is about the measurement of temperature. And the temperature is a very, very important parameter of physical quantity to human body, because every one of us could be treated as a storage of thermal energy, right? Nobody of you could claim that you have a 0 thermal energy. If you have a 0 thermal energy, it means what? You understand the answer, right? So actually, our body has a temperature. And in particular, we must control our body's temperature within a limit around the 36 degrees, right? So then you will see our body is a very, very precise controller of temperature, right? If let's say our body temperature go far below 36 degrees or far beyond 36 degrees, then we were in trouble, all right? So this is something very, very familiar to every one of us, because every one of you actually constantly doing temperature control, all right? So if you start to think about your body, actually, okay, there's a feedback control system based on the input of temperature, right? So this is something that every one of you should be familiar with, all right? It is good anyway for us to go through the physics behind the temperature Then we are going to study the indirect way of doing determination of temperature, and our key focus is on direct measurement. Okay, and to study the physical principle behind the design of a measurement and the sensing system for temperature. Right. So let's start with the basics. Okay, or mathematics or basic physics behind temperature and the mathematics behind temperature, right? Okay, so besides our body, because just now I mentioned, actually our body is a temperature control system, all right? Because the temperature is a very, very important parameter of the human body, all right? And similarly in industry, temperature is very, very important because in manufacturing, basically, it means what? Manufacturing means a transformation of an input material into output material of desired geometry or shape, etc. All right, that should be one of the major activity in industry. Then how to transform the geometry of a solid? Okay, then the answer is to increase the temperature so that to facilitate, okay, the transformation of input material into output material with a different type of geometry. So here you will see for injection molding, the input material should be powder or solid. Then by adding increase the temperature, then the solid become liquid. Then it's easier for us to inject the liquid into the cavity of a die. Then we let it to cool down. Then liquid will become a solid. Okay, so this is a typical process of doing injection molding. All right, and for the handling or machining or some very, very hard object, so you will see it is always good to increase the temperature. Then in this way we can easily modify the geometry of solid object. All right, and then in other process, so temperature control is very important. All right, so because in the physical world we understand every entity could be exist in one of these four states: solid, liquid, gas, and plasma. All right, so actually it is easier for us to to transform, okay, manipulate liquid. Liquid is very easier for us to change the geometry. All right. So then how to make a solid to behave like a liquid? The only way is what? To increase the temperature. Then how to increase the temperature? Add in thermal energy. All right, but later on we will see the detail. All right. Then inside the building is the same. Also our body can control our body's temperature. However, we need the help of the environment. If let's say you have a room, the temperature inside the room is 100 degrees Celsius. You enter such a room, I do not believe you could survive. Okay, because the control capability for temperature by our body has a certain limit. So we need the help of environment, okay, or the space to assist us. So one way is to control the room temperature to be at, for example, 25 degree or 26 degree. So therefore, you see the control of the temperature in the manufacturing environment, in the office building, in hospital, in our home, in the shopping mall, etc., are very important. So you see, so a lot of application for temperature control in building, which may be related to factory, to school, to administration, office, and to our home, to hospital, etc. Right? So this is straightforward for you to understand. Okay, the importance of doing temperature control. Otherwise, it will be very difficult for us to survive. Okay, and you see, for animal and the human being, we need the temperature control because if the variation of the temperature go beyond certain limit, it will be painful for us to survive. Then similarly for vegetable, for plant, they also need the temperature to be controlled within a certain limit. all right, in order to survive or to grow. Okay, so immediately you see a lot of application with temperature controller in agriculture. Okay, so because the plant, vegetable also, okay, need to control the temperature within a certain interval. Okay, so similarly to the case of animal and the human being. All right, okay, so it is quite easier for you to understand. All right, so it is extremely important, okay, for us to control the temperature. Then how to control the temperature? We must have a sensor for temperature, right? And actually this lecture basically introduced to you the third energy, the third popular energy. So far, we have studied physical quantity which are related to electric energy, and also we have a study physical quantity which are related to mechanical energy. Now, temperature actually is one of the physical quantity related to thermal energy or heat in layman term. Okay, so in layman term we use heat. Okay, the technical term is thermal energy. All right, and one of these two important physical quantity which describe thermal energy is temperature. Now you see temperature has an equal importance, okay, like force for mechanical energy and voltage for electric energy, right? And again, you will see the statement made by Nikola Tesla, right? So he says that if you wish to understand the universe, you just need to have a 3 keyword, okay? Energy, frequency, vibration. Then here today we talk about the thermal energy, okay? So it is also true to human body. Why do we need to control our body's temperature to be roughly around 36 degrees, all right? It's because we must keep the energy level of our body at a certain value, all right? It should not go below or should not go beyond, okay? So go below, that means we are in trouble. Go beyond, we are also in trouble, all right? So energy, very important, all right? Okay. And then there's an important application of thermal energy with the invention of a steam engine, okay? That changed the landscape of transportation and also automation in the factory, okay? So this video basically explained to you about this important invention of a steam engine, all right? The steam engine is what? Is to make use of temperature to transform water into vapor, then use the vapor to drive, to produce mechanical movement. So basically there's a transfer of a transformation from thermal energy into mechanical energy. Then with mechanical energy, then we can produce a rotary motion, linear motion, okay? And with the motion, again, we can do a lot of work, all right, okay?
Of human existence, the most significant catalyst for growth has been our ability to draw energy from our world. Taming fire gave birth to the modern human, and drawing power from the wind allowed early explorers to travel the world. But today, we're going to explore the history and science behind one of humanity's greatest inventions, the steam engine. The evolution of the steam engine completely revolutionized our society. It opened new avenues for trade and caused mass migrations of rural populations into the newly industrialized cities. What I found most fascinating was the lessons its evolution taught us about science and engineering. This is one of the first practical steam engines, and it was used to pump water. The engine was incredibly inefficient. This machine was not going to start any industrial revolution, but it found a niche in coal mining, where its fuel was cheap and readily available. To investigate why this engine was so inefficient, let's first talk about how it works. The engine takes energy stored in coal and converts it to heat. That heat is used to form steam, which expands into a piston cylinder, causing the pressure to increase and forcing the piston to rise against atmospheric pressure. No mechanical work occurs on the stroke, because this chain can only transmit force in tension. The power stroke occurs when cold water is sprayed into the cylinder. This lowers the temperature, causing the pressure to drop. Atmospheric pressure now pushes the piston back down. We want to be able to quantify how much work is being done per cycle of this engine. To do that, we plot the pressure and volume inside the piston cylinder for one cycle, like this. The area inside is the work done, but this is the idealized PV diagram. In practice, there is a lot more energy being wasted. We lose a big chunk here because the steam is prevented from expanding to its full volume. A lot of energy is lost to the environment too. This is clearly visible with thermal imaging. The effect is made worse by cooling the entire cylinder with cold water. So an immediate improvement is to make a separate condenser. Here the steam can be cooled without cooling the entire cylinder. There are a lot more inefficiencies involved that reduce the total work done. Many of them are unavoidable, but we can improve the situation by upgrading the piston cylinder. The manufacturing techniques needed to bore accurate and strong piston cylinders were not available in the early days of the steam engine. That changed when John Wilkinson invented this machine. This boring machine allowed for precise machining of solid iron cylinders, which reduced steam leakage and made the piston cylinder stronger, thus allowing the max pressure to rise. We are starting to see a steam engine capable of sparking an industrial revolution. But this reciprocating motion isn't much use for most applications, especially with this flexible chain connecting them. What we need is rotational motion, which requires a different setup. To convert this linear motion to rotational motion, we need a crankshaft and connecting rod. We have turned this piston cylinder on its side, so atmospheric pressure can no longer force the piston back down, so we need to use steam on the return stroke. This requires a control valve to control when the steam enters and leaves each side of the cylinder. The valve is controlled by a cam. The steam engine is now working on both strokes of the engine, improving its efficiency and power. But piston engines like this do not produce constant torque. They'll pulsate in speed and torque during a single cycle, like this. This can cause vibrations and jerky movement. We can reduce this with the use of a flywheel, which stores rotational energy with inertia and evens the torque out. It's essentially a mechanical battery. David Robert demonstrates this beautifully with a V8 solenoid engine of his own creation. Here you can see the engine will continue to rotate without additional power, but the engine comes to a dead stop without a flywheel attached. The development of steam engines taught us a lot about thermal and mechanical efficiencies, and you may think that steam engines have become obsolete, but nearly all of our large power stations still use steam technology to convert heat energy, whether that be from coal, nuclear, or solar, to mechanical energy. The technology has simply evolved into an even more efficient form with steam turbines. Thanks for watching.
Right, so you see, this is a very important application, okay? With the use of thermal energy, then convert it into mechanical energy, and eventually convert it into electric energy. All right, so thermal energy is very important in industry and also in the society. Therefore, it's very important for us to understand the basic physics behind the thermal energy, and also the physics behind temperature and the equation or mathematics behind temperature, etc. So let's start with the phenomenon of the heat. Okay, so heat basically is energy which could be transferred from one body or hot body to the cold body. So you will see heat is not the substance. Okay, so it's kinds of energy. All right, and heat is also a measurable quantity because there are two important parameters which describe thermal energy. One is the temperature, another one is the flow rate of heat. All right. So mathematically, we should be able to describe thermal energy. All right. And then we have to find the source of thermal energy. Then in the solar system, we know sun basically is the primary source of thermal energy inside the solar system. All right. And we should not treat the heat as a material substance because it is not the material, okay? Because heat could be transformed into mechanical energy. So basically it's a kind of energy, all right? And when we transfer energy into, for example, water in solid, then water will become the state. of liquid, right? So if we add in more heat, then the water will transit into the state of a gas, okay? So in the form of vapor or steam of water, etc. So clearly, heat is energy. It's not the substance, right? And heat basically is a layman term which refer to thermal energy, right? And you will see this is a typical example of transfer heat into the solid object with a very high level of hardness, okay? So when the object is very hard, it's difficult for us to change its geometry. However, when we increase the temperature of the solid object, then it's easier for us to change its shape, right? So this is a typical application in industry, all right? And then for any system, okay, so heat could be transferred in, transferred out from any system. For example, our body is we could consider is a thermal energy system. Okay, we can absorb the heat from external environment, and also we dissipate heat to the environment, right, through the vaporization of water. Okay, so then there's a conservation of energy. For example, we inject this amount of energy into a system, and this system will do contribute this amount of energy through the work done back to the external system. Then what is the net change of energy? So we have this input, this is the output, then the net change, okay, of energy inside the system is equal to this one, all right? And this net change of energy will basically accumulate inside the system, all right? And this accumulated energy could be manifest in the form of increase of temperature. Then we want to know what is the temperature, okay? Because when the heat build up, immediately we feel, okay, there's a value change, okay, from a specific quantity. This quantity in layman term, we call it as a temperature, okay? Because we may say, this has become very hot, become very cold, become warm, okay? You see, we use all these layman term to describe this phenomenon of increase in temperature. All right. So then we need to know what is the temperature. All right. So temperature basically in layman terms creates a sensation of hotness and coldness. All right. And temperature is a physical quantity. It is an independent physical quantity which is associated to thermal energy, and is one of the two major physical quantity which describe the amount of thermal energy, right? And temperature is a scalar, so we can describe it, okay, along axis for reference. Then it is like the case of pressure, okay? So for pressure, we have absolute zero pressure, and we also have another reference for zero, which is equal to the atmospheric pressure, right? Then for temperature, it is very much similar to the case of pressure. So we have absolute zero, absolute reference for zero, and also have another reference for zero, all right? So then we have a zero in terms of the Kelvin. So this is absolute zero, all right? Then because this reference is not so intuitive, you see the gap is a 273. So like for layman, it is not intuitive to interpret the value of a temperature. This is why we are used to this reference Celsius, because 0 Celsius corresponds to the temperature at which the water in liquid will become a water in solid. All right, so zero temperature. All right, so that one is more intuitive to layman. Okay, so then we have these two natural reference for zero temperature. However, you may heard of Fahrenheit, but actually this is not the reference for zero because you see the conversion between Celsius to Fahrenheit. So it's not just to A in the offset. It's not in the temperature axis. So we identify a point. Okay. So you see, this is a transformation. So actually, the axis for Fahrenheit basically is another scale, because you see we have a scaling factor of 9 divided by 5. So actually, this axis, this space, one-dimensional space, has been scaled up, okay, by this factor. So then we should not consider it as the same temperature space, all right? So because this axis basically is applicable to both unit of measurement, such as Celsius and Kelvin. However, it is not applicable to the unit of measurement of Fahrenheit, because Fahrenheit you must have another reference for temperature, okay, because the scale is different, all right? So strictly speaking, so we should not consider this as a reference for zero, because it's another temperature space, right? Because later on in one lecture, in one future lecture, we are studying acquisition or measurement of a visual signal. Then we may talk about the color space, right? Then you see we may have a different color space, okay? So these color space are the transformed three-dimensional space, okay? So you should not consider them to be the same, right? So each color space has their own reference for origin, right? However, with the unit of measurement Kelvin and the Celsius, they could be superimposed together because they only have an offset, okay? So they are in the same temperature space, if we use this term, okay? Celsius and Kelvin belong to the same temperature space, all right? And Fahrenheit belong to another temperature space, right? Okay, so this just for you to know, all right? Then how to do the conversion? So basically, we just need to know the conversion between Kelvin and the Celsius, and also the Celsius and the Fahrenheit, okay? Because these three are the most popular unit of measurement used in the society and the industry. Okay, so here basically you just follow these two formulas in order to know the conversion, okay, between the unit of the measurement for temperature, right? And temperature is, okay, just now already mentioned, okay? So temperature describes the sensation about the hotness, coldness, okay? And the temperature has a space, and in this space, there are two reference for zero value, all right? And actually, temperature is one of the important physical quantity which describe the amount of thermal energy, okay? So temperature times the flow rate of heat is equal to thermal energy, all right? So then at the atomic level, so actually temperature is a manifestation of a kinetic energy, so it's a vibration. So when the temperature is high, then the kinetic energy is strong, okay? So then you will see in a three-dimensional space like X, Y, Z, in each direction, so there is a kinetic energy. That means the kinetic energy component in the X direction, in the Y direction, in the Z direction, okay? And each kinetic energy component is a function of a temperature. We will add them together, so then you will see kinetic energy basically is proportional to temperature. So therefore, temperature basically is indicator of kinetic energy at the atomic level, all right? So it's quite easier to understand. And temperature is a physical quantity which play a similar role like voltage for electric energy and force for magnetic energy, right? Because for voltage means what is electric potential, all right? Then the force could be considered as a magnetic potential, because with the force, so we have this potential to do work, okay, to transfer energy to another body. Then for temperature is similar, it's kind of a thermal potential, and this potential indicate the capability of transfer in or absorb thermal energy. Okay, if we have an object at a higher temperature, another object at a lower temperature, if we put these two objects in the proximity, then you will see there's a heat transfer from object at a higher temperature to object at a lower temperature. All right. And here is one more example. Okay, so when there's a temperature difference, this corresponds, there's a difference of a thermal potential, then the heat will flow from a higher potential to lower potential. Okay, for example, in this case, in the right hand side, we have a higher temperature, then slowly in the left hand side, gradually the temperature will drop to T3, T2, T1. Then there's a flow of a heat being transferred from left hand side to the from right hand side to the left hand side. All right. Then mathematically we can just imagine there is a thermal resistance. All right, and then we can consider temperature like a voltage and thermal resistance like a resistor. Okay, or resistance in electric domain. So you will see temperature goes to pass through thermal resistance, then you will reach this temperature of a T4. Then again, the wall here will also provide this thermal resistance. Then inside vacuum, there is also thermal resistance. Then in the left wall, there is also thermal resistance. Then from the solid to the air, then we can imagine there is also a thermal resistance, right? So then you will see, actually we can use electronic circuit to represent the phenomenon of flow of heat. You just imagine the flow of heat is like a flow of electron, all right? Then temperature is similar to voltage. Then it's easier for you to understand, okay? The phenomenon of thermal energy when it passes through, okay, different material, right, in space, right? And then, okay, so this just summarizes, okay, the observation in the previous slide. So the difference in temperature will cause transfer of the heat within a same object or between different objects, right? So, and here is an example. So at the one side, we have a higher temperature, another side, we have a lower temperature. Then you will see the flow of the heat, which will pass through this object, all right? So, and then what will be the exact phenomenon of doing the heat transfer, okay? So actually here already highlighted to you, okay? So at this interface, so this is the interface between gas and the solid, and this is the interface between, and the inside here is within the solid. Then here is an interface between gas and the solid, all right? Then this is the reason same media, either liquid, gas, or solid, all right? Now you see the transfer, heat transfer across the interface between gas and the solid. Then this is the heat transfer between the interface of the solid and the gas, all right? So basically, there are three phenomena. One is called convection, another is called convection, and the third one is radiation, all right? Convection means heat transfer within a solid, within the object entity, or between object in close contact. Okay, you have object one, object two, they have a close contact, all right? Within the solid, okay? So this is the convection. Then convection means heat transfer either from gas to solid or solid to gas, right? So the object, two objects are in different state. Okay, you can say convection means a heat transfer, okay, within object in solid state, all right? Then convection means heat transfer between a pair of objects in two different states, right? Then third one is radiation. Radiation means because among the electromagnetic wave for certain frequency, for example, we call them as infrared wave. So actually, they are the source of the heat. They can carry the heat. So then this is another way to transfer the heat through the use of electromagnetic wave at a certain frequency or wavelength, right? So these are the three type of heat transfer, right? So then another phenomenon which are related to the temperature is when there's a change of a temperature, then the length of a material will also change, okay? So there is this phenomenon of expansion or contraction, right? So actually this phenomenon could guide us to design sensor. For example, we can convert temperature into variation of the length, then variation of the length into either resistance or voltage or current or something like that, or capacitance or inductance, all right? Then we can come out with a design solution for temperature sensor, right? Okay. And you may wonder why we do not use this working principle. Later on, you will see the answer is a cost or relative cost, because we have other solution which is less expensive than this one, and it gives a good performance at the output. So therefore, we have other two popular solution to guide the design of temperature sensor. Okay, but in theory, if let's say we don't care about the cost, so immediately this is a design principle for us to follow. All right, and another phenomenon is about the change in volume. If an object can change in one dimension, in theory, it can change in three directions, right? So if we never restrict the change of the geometry in three directions, then this object, when the temperature increase, the object will change geometry in three directions. However, we can restrict the change of geometry in a single direction. For example, the object can only move within a tube. Okay, then it can only change the length in one direction, right? So, but if we never restrict the change of the geometry in any direction, then the heat will make it change to the geometry in any direction. So this is a typical example, all right? So then you will see, actually we have an equation which relate the temperature to other physical quantity. Okay, therefore we may want to know what are the useful equations for us to use in order to calculate temperature. Okay, so here, so I'm going to show you some useful equation. Okay, first one is equation of ideal gas. All right, so you know for equation of ideal gas, the temperature is proportional to the pressure. Temperature is also proportional to the volume, and this is the molar number, and this is a constant, it's a coefficient. All right. So then we may have a different scenario. For example, we can make the pressure to be constant. We can also make the volume to be constant. Okay. Because the temperature is a function of a P and the V. If we want to study one-to-one relationship, so we can keep P to be constant, then we know what is a TV relationship. We can keep a V to be constant, then we want to know what is a PT relationship, right? So this is one useful equation for us to use. Another useful equation is about this internal thermal energy equation. So actually, every rigid body is a storage device for thermal energy, all right? So normally in the universe, except the black hole, all right? So except the black hole, all the physical entity must have a value of a temperature which is not equal to 0, all right? For human body, our body temperature is not equal to 0, all right? So therefore, basically, temperature indicates the amount of internal thermal energy stored inside the physical entity. Then what should be the equation for us to calculate this amount of thermal energy. So actually it's this one, okay? The amount of energy stored inside entity is proportional to the mass, proportional to the temperature. But this equation showing you the variation in order to increase this amount of temperature, what should be the additional heat to A inside this entity, all right? So if we just look at exact equation, so the heat should be equal to proportional to temperature, proportional to the mass, and in front we have a coefficient. This coefficient is called as a specific heat, right? So this is also a very useful equation for us to use. And then we have an equation of convection, right? So equation of convection basically means the flow rate of the heat, okay? So it's easier to understand that the flow rate of the heat is proportional to the area in which the heat will pass through. Okay, the larger the area, then will bigger the quantity of the flow rate will pass through. And also proportional to the temperature difference, because temperature difference is equal to thermal potential difference, right? Okay, and inversely proportional to the thickness, okay? Because if the wall is very, very thick, then it's difficult for the heat to travel through, all right? So it makes sense for you to understand. Then in front, we have this thermal conductivity coefficient, K. So this is also a very useful equation, and it's quite straightforward for us to understand, all right? Then for convection, convection is a heat transfer between two entities in two different states, all right? Then in this case, the amount of heat which flow, okay, from one object to another object in two different states. One is a solid, another is a gas, all right? So it's proportional to the area in which the heat will pass through. So it makes sense, the larger the area and the bigger amount of the heat will pass through, all right? And also proportional to the temperature difference. Then in front of it, we have a heat transfer coefficient of H, right? So then for third one, so third one basically is the amount of energy, the power transmitted out by electromagnetic wave at the infrared frequency. Then, okay, so then this energy power. So basically, so power is also means the flow rate of the heat, right? Because we can talk about the electric power and mechanical power. So mechanical power is equal to mechanical energy per unit time, all right? And electric power means electric energy per unit time, all right? Then thermal power, you can say, okay, thermal power equal to thermal energy per unit of time. But here, we do not use this term, thermal power. Basically, we use a flow rate of heat. So flow rate of heat, strictly speaking, should means thermal power, okay? Thermal power equal to thermal energy per unit time, all right? So power basically means energy per unit time. So it's the same thing, all right? So it means the same thing of flow rate of heat, okay? So it's proportional to the area, okay? And then proportional to the difference of temperature, okay? Raised to the power, which is equal to 4. And Tc is a temperature in the space, okay? So in temperature in the space, and this is the temperature of a source of radiation, okay? So energy of the source, if this one is higher than the ambient temperature, then there's a radiation, okay, goes to the environment, all right? So this is a formula for us to use, all right? Then when we know, if let's say we can measure expansion of a material in one direction, then you will see the change in the length is proportional to the change in the temperature, right? And it's proportional to the initial length, and in front of it, we have this expansion coefficient, okay? So linear expansion coefficient. And similarly, if an object can change its volume, then variation of the volume is proportional to variation of the temperature, and also proportional to the initial volume, V0. And in front of it, we have a coefficient, which is called volume expansion coefficient of this material, all right? Okay, so that's all about the basic physics. behind temperature and the basic mathematics behind temperature. Now we are ready to look into the solution for us to do indirect measurement of a temperature and direct measurement of a temperature. Indirect measurement of a temperature means computation of a temperature if we know related value, or we know the value of related physical quantity, then we should be able to directly compute the value of the temperature. All right. So this is the first example. In this example, then you'll see inside the container initially, we have the volume which is equal to 22.4, and the number of the molar of the gas inside is 1. Now we add in gas inside, then the volume will expand to 44.8, and the number of the molar number increase to 2. Now we want to know what is the temperature inside this container. And here on top we put the piston, and this piston, the cover can freely move. So it means what? Inside the gas, the pressure is equal to 1 atmospheric pressure. Okay, so this means inside here it is also 1 atmospheric pressure. And here we ignore the weight of this cover. Okay, just ignore the weight of the cover. Okay, so then in this case, actually we know the volume, we know the pressure, we know the molar number, we know the coefficient. All right, so then in this case we can directly calculate what should be the temperature inside here, and then we get this number. But pay attention, the result here is an absolute value with respect to the absolute zero reference. Okay, so unit of measurement here is a Kelvin. If we want to know the temperature relative to another reference 0, okay, in terms of Celsius, then we need to do a subtraction between this value and the 273. All right, so in this case, the temperature is equal to this value in terms of Celsius. All right, so and this value is relative to the 0 degree, which corresponds to the temperature at which water will change its state from liquid to solid. All right, so 0 degree of Celsius, and this is relative to 0 degree in Kelvin. All right, so this is value relative to 0 degree in Celsius. All right, so here's another example. Okay, so inside this tube, okay, so we have a certain amount of mercury. Then you will see mercury can only expand in one direction. All right, so of course it can expand its volume, but this expansion of the volume will be reflected by the increase in the height inside the tube. All right, so because this is a liquid, so it can expand in all directions, but it can only move up. Okay, inside the tube. All right, okay. So its volume is 200 centimeter cube at the 20 degrees Celsius. The volume expansion of the glass is negligible, and the coefficient of volume expansion of the mercury is this one. If we observe that the volume of the mercury has increased by this amount, all right, then what is the value of the temperature, right? So then, okay, we apply this formula. Volume expansion is proportional to temperature difference, proportional to initial volume, proportional. Then in front of it, we have this volume expansion coefficient, all right? So the temperature increase is what we want to determine, all right? So both sides divide by beta V0, then shift T0 to the left-hand side, then we swap the equality, then we get the T equal to T0 plus theta V divided by beta V0. And T0 we know is 20 degree, and okay, 20 degrees Celsius. Because here we can talk about the Celsius or Kelvin, because it is relative. If we add in 273 here, so then we get the later on we minus 273. Okay, if we use a Celsius to serve as a unit of measurement, then this result is equal to, okay, Celsius, because this term corresponds to the increase in value. All right, because there's no scaling factor. The scaling factor for Celsius and the Kelvin is 1. Okay, so their variation is the same. Variation in Kelvin is equal to variation in Celsius. All right, so this is why we do not need to convert it into Kelvin. All right, so because this is a variation in Kelvin or Celsius. All right, so you put in the value, then finally you get this answer. All right. Okay, this is one more example, and then in this case we have a pan. Inside we have a 1.5 kg water like this temperature, and there is a specific heat capacity. Okay, the specific heat capacity of water is 4,190. So here we just consider the water is a storage device of the thermal energy. Okay, then we can transfer thermal energy from the store, okay, into the body of the water. All right, and then this question tell you what is the coefficient C, specific heat of water. And during the process of the boiling the water absorbs the heat at this flow rate of the heat. This is the flow rate of the heat. Then what is the temperature of the water 1 minute later? 1 minute corresponds to 60 seconds, right? So let me apply this formula, okay? So the temperature increase is the amount of heat we must add in should be proportional to the intended change in temperature, right? So, and proportional to the mass, and in front of it, we have this specific heat coefficient, all right? And this is what we want to know, okay? After 1 minute, what is the temperature? Then what is this one? This is the amount of heat transmit, okay? Transfer into the body of the water, okay? So let's say the flow rate of a heat transfer is 500 joule per second. Now you see the duration is 1 minute. 1 minute is equal to 60 seconds. So that means this one should be equal to 500 times 60 seconds, right? So within 1 minute, we have this amount of heat being transferred inside the water, right? Then what should be the increase new temperature, right? So then this one divided by the mass divided by the specific heat coefficient, then plus is the initial temperature. So then you will see the increase of the temperature is by 4.77 degrees Celsius, right? Okay. And here is another example which, okay, ask us to determine the temperature at the outside wall, okay? So let me say this is the inside the room, the temperature, okay, the room temperature is 26 degrees Celsius. Assume that the thickness of the wall is 20 cm, thermal conductivity of the wall is 0.19 watt per meter Kelvin, all right? And if the energy consumption of the wall means what is the flow rate of the heat which will pass through the wall, okay? So it's 50 watt per meter square, okay? Then what is the temperature outside the wall? So you see outside should be at the lower temperature, so we have a T1 minus T2, right? So, and then this is a typical example of convection. So there's a flow of thermal energy due to the temperature difference at the left-hand side of the wall, which is a T1, at the right-hand side of the wall, which is a T2. So then the flow rate of the heat is proportional to the temperature difference, inversely proportional to the thickness. And in front of it, we have the thermal conductivity of the wall, all right? Then what should be the amount of the flow rate of the heat? Flow rate of the heat is equal to dq over dt, okay? Because q is amount of heat being transferred, then the amount of the heat transfer per unit time, so it's a dq dt. And the A normally is inside here because this one is proportional to the area in which, okay, the heat will pass through. So now we shift A to the left-hand side, okay? Then we have this equality. And this energy consumption is given to us, then it is 50 watt per meter square. So basically, this value corresponds to this expression. All right. So, and then, okay, from this equality, then both sides times L, both sides divided by K. Then we can shift T2 toward the left-hand side. Then this left-hand side turn to the right-hand side. Then we have this expression, T2 equal to T1 minus 50 times L divided by K. So you put in the value, then we should be able to get this answer. So outside should be negative 26.63 degrees Celsius, right? So then here is one more example about the heat transfer, okay, between two objects of the same state, because you have a solid, this also is a solid, then in the surrounding, we have a perfect insulation, a thermal insulator. It's like a conductor in electric domain, we have an insulator to prevent the electron to flow out. This is to prevent the heat to flow out, okay? So then we have a steel bar and the copper, all right? And the lengths are the same, so 20 cm, 20 cm. So at the end of the copper is a 20 degree. At the another end of the steel is 100 degrees Celsius, all right? The cross-section area of the two bars are the same. Thermal conductivity of steel is given to you, and the thermal conductivity of copper is given to you. Assume that the free end of the steel bar is 100 degrees Celsius. The free end of copper bar is 0 degree. Then what is the temperature at the interface or at the junction between these two solid metal, all right? So then in this case, we apply this principle, so conservation of energy. So it means that the flow of the heat inside the copper should be equal to the flow of the heat inside the steel, okay? So this is the conservation of energy. So this is what flow of the heat inside the steel. This is the flow of the heat inside the copper. So they must equal. Then what is the flow of the heat inside the copper? So it is proportional to temperature difference, inversely proportional to the length, and proportional to the area. Okay. Then what is the flow rate of the heat inside the steel? So this one is proportional to temperature difference, inversely proportional to the length, proportional to the area. So area can be cancelled out. Then we just want to determine what should be the T. So we arrange this equality, we should be able to get this formula. T equal to 100 times thermal conductivity of the steel divided by the sum of both metals thermal conductivity. Then we put in the value, we should be able to get this answer. So that means inside here, the temperature is 11.535 degrees Celsius. All right, so this is a typical example for us to calculate the temperature if we know the value of related physical quantity. All right. Now, our major focus in this course is to understand what should be the physical principle for us to apply in order to guide the design of a measurement and the sensing system for temperature. All right. So actually, there are many principles in theory, and however, in practice, these are the two popular design principles. All right. And why we prefer these two popular design principle. One is about the cost, okay? Second is about the performance, because these two design principles give us the best offer in terms of performance cost ratio. Of course, you can make use of the length expansion method, the volume expansion method, and even you don't care about the cost. For example, you can use infrared based on the radiation. Okay, because every body is a storage device of thermal energy, and such storage device of thermal energy could transmit out okay, or transfer out the thermal energy by radiation. So therefore, we can use expensive thermal camera to capture image, calibrate it, then to measure the temperature. Okay, so if let's say your industry has many locations to monitor, to measure temperature, then the investment will be very high. Understand? Okay, so here we just talk about the solution which give us the best performance price ratio, right? So first principle is to directly convert temperature into DC voltage. Then immediately we can make use of a microcontroller to interface it. Okay. Then second principle is to convert temperature into resistance, then from resistance into DC voltage. All right. So these are the two popular principles for us to follow. Okay. And the first principle basically is highlighted here. So actually there's a phenomenon about the thermocouple. So we put the two conductor of two different types, okay, together. So at the two ends, we link them together, okay. So one end we call is a cold end, cold junction, and then we have a hot junction. And basically this is serve as a reference, okay. And this one is to serve as to do the sensing, right, to sense the temperature in the specific location, right. And then if we put the two conductor of a different type together, then we observe voltage, okay, which will form up, okay, when there's a difference in temperature, okay. So if this temperature is equal to this temperature, then there's no voltage. As long as there's a temperature, okay, a difference, then there's a flow of electron. So this indicates there's a flow of an electron. Then it's equivalent, there's a voltage, right? Then for second principle, we make use of, this is a very cheap solution because we have a special type of resistor. Resistance is a function of a temperature. So then we just make use of such a resistor. And in addition, we can create special conductor in which the resistance value is a function of a temperature. Then we call this conductor as RTD, or RTD means a resistance temperature detector, right? So they are quite similar, but however, this is there's slightly difference there, okay? So then how to apply principle one to guide the design of measurement and the sensing system for temperature, right? So the idea is to convert temperature directly into DC voltage. Then we make use of a microcontroller because we know that all microcontrollers are programmable digital sensor of the voltage, right? Then how to implement this additional module here, okay? So the answer is to use a thermocouple, right? So the thermocouple will provide voltage, and the output voltage is a function of temperature difference between these two junction, okay? So we have a cold junction, we have a hot junction. Cold junction means ideally maybe it is at the 0 Celsius, reference 0 in Celsius, okay? And if it's not, then we can adjust it, okay? It could be at any reference value, okay? Then this is the point on the measurement for the temperature, right? So this explained to you. So basically we put the two conductor of different type together, then we have this magic result, okay? When there's a temperature difference, then electron will flow inside, okay? So of course, it is always good to use the copper. Why to use copper? Because inside the copper, we have more than 30 electron, okay, orbiting around inside the atom. So then we have a lot of electron, okay? You should not use a material with very few electron inside, then the current will be very small, all right? So copper is ideal candidate to serve as one metal, okay? One conductor. Then another one should be or to use iron. Iron is also a material with a lot of electron inside atom, right? Okay, so then here just show you example about the thermocouple's body design. Then you will see we have external casing, okay, and then we have a hot junction. This is a sensing junction. Then we also have a reference junction. Reference, it could be reference for 0, okay, temperature. In case it is not reached the 0 temperature, we can calibrate it, okay, to have a reference at any specific value, all right? And then the output voltage is proportional to the temperature difference between hot junction and the cold junction, right? So then how to pick up the voltage signal? So, and this is a solution that we can use amplifier, right? So you will see this is a thermocouple, okay? So this is a sensing junction, we call it hot junction. And this is a cold junction, we call it as a reference junction, all right? So if let's say we want to calibrate this sensor at the when it's a 0 temperature, then this output 0. So that means we can put this one at the 0, reference temperature 0, okay? For whatever reason, this one may not be 0, okay? Then in this case, we can aim voltage to compensate so that the VC plus V1 equal to 0, then this output 0, right? So you see, we can always do hardware compensation to make sure that, okay, when this one is at 0 temperature and then output is 0, then when it is at the, okay, any other temperature, then the output should not be 0, all right? So this is just for you to know, okay? So then here just illustrate, this is ideal situation because in practice it's difficult for us to place this one in 0 temperature reference location, because in this way, because during the calibration, this may be at the wrong temperature, okay? Then we place this one inside the 0 temperature, inside the ice, for example. Then we have a reading here, because actually, because the T1 is not equal to 0, but T2 is equal to 0. Then we can make this one to become 0, right? By aiding compensation, okay? So then when this one is in another temperature, then this should not be 0, then the value come out, okay? So this is the ideal situation because it's difficult for us to actually maintain this cold junction at a 0 degree. We cannot put the refrigerator there, that will be very expensive, okay? So this is an electronic solution for us to achieve similar results. So this is an ideal situation. That means one junction is at the 0, okay, reference temperature. Then here is a sensing junction at the point in which there is a temperature on the measurement. All right, so you see we have an electronic solution. Okay, so then you see principle 1 is quite straightforward. Okay, so we have a solution. And then how about principle 2? Principle 2 is to convert temperature into resistance, then convert resistance into voltage, then we measure voltage. All right, so like in this case, we have a 2 module. First module, external module to the microcontroller. First is to do the conversion from temperature to resistance. The second module is to do conversion from resistance to the voltage, right? So then what is the solution for this one? The good news is to use thermistor, all right? So this video explains to you the behavior of thermistor.
A little electrical component for measuring temperature called a thermistor. They originally needed it for measuring the water temperature in a set of experiments, determining if cold water boils faster than hot. But just for fun, I also got to turn on this PC fan when the heat was too high. What's a thermistor? The thermistor is usually a ceramic or polymer material with 2 wires connected to it. The key is that the thermistor's resistance changes with temperature. With some, the resistance increases as the temperature increases. Those are called positive temperature coefficient, or PTC thermistors. With others, the resistance decreases as the temperature increases. Those are called negative temperature coefficient, or NTC thermistors. I couldn't find a thermistor locally, but some quick research turned up that automobile coolant temperature sensors are just thermistors in a protective case, which was a good thing since that saved me having to make a case of my own. With this one, there's only one obvious place to connect to, this threaded part. So where do the 2 thermistor wires go inside? Well, one goes to the threaded part and the other goes to the brass case. So I wrapped one wire tightly around the case, and after attaching a ring terminal to a wire, and finding suitable nuts, I attached another wire to the threaded part. I then connected up a meter and put it on the resistance scale. Remember, the resistance changes with the temperature. I put my fingers on the probe part and it started to heat up. Sure enough, the resistance on the meter started to decrease as the temperature increased. So it contains an NTC, or a negative temperature coefficient thermistor. To be useful, I needed to know what resistance matches what temperature. Unfortunately, I couldn't find a resistance temperature table for this particular one, so I had to make my own. To do that, I prepared a tall container, this soda can with all the paint sanded off. I filled it with water and put the probe part of the sensor in the water. I also put in my kitchen thermometer. The long length of my thermometer is why I went with a tall container. For my purposes, I needed to know the resistance to temperature values for temperatures near the freezing point of water. So I put the whole thing in my freezer until the thermometer read near 0 Celsius, or 32 Fahrenheit. Then I took it out, connected my meter to measure resistance, and put it on my stove heating element. I then started recording the resistance on the meter and the corresponding temperature on the thermometer as the stove element heated up the water. I stopped once it reached boiling, which is 100 Celsius or 212 Fahrenheit. And here's the chart drawn using the data from my table. As you can see, the resistance decreases as the temperature increases. You can also see that it's a curve. The whole reason I'd gone through this process was to do some experiments to determine if cold water boiled faster than hot water, as some people think it does, and to find out why that myth might exist. That resulted in this graph of water temperature as it was heated up over time. But that's a whole other topic, which I cover in another video I'll point out later. Here's the fun I had making a PC fan turn on when the thermistor gets too hot. First, here's the circuit without the thermistor. It's very simple. The positive from my homemade power supply goes to the positive of the fan, and the negative of the fan goes back to the power supply. When I turn on the power supply, the fan starts spinning. Now here it is with a thermistor. The positive from the power supply goes to one end of the thermistor. The other end of the thermistor goes to the positive of the PC fan, and the negative of the PC fan goes back to the power supply. But this time, when I turn on the power supply, the fan doesn't start spinning. That's because the thermistor is nice and cool at room temperature, and so it has a high resistance. The fan needs a certain amount of electrical current going through it in order to spin. But the higher the resistance in the thermistor, the lower the current is going through the fan. And the resistance of the thermistor is high enough to make that current too low. Now I use this hair dryer to heat up the thermistor. That causes the thermistor's resistance to decrease. As it decreases, the current increases. And when the current's high enough, the fan starts spinning. Notice that the fan is blowing on the thermistor, making it cool off more quickly. Here I'm showing the airflow direction using this tissue paper. As the thermistor cools, its resistance increases, and that causes the current going through the fan to decrease. After a minute or so, the current is too low to keep the fan spinning, so it stops. Well, thanks for watching.
All right. So that video basically gives you a good idea about the nature of a thermistor and the use of a thermistor. Thermistor basically is a special kind of resistor, and in practice, there are two types of thermistor. One is called PTC, another is called NTC. PTC means when temperature increase, resistance value increase. NTC means when temperature increase, resistance reduce. All right. So this is a typical sensing element for us to pick the variation of temperature. All right. And this is background knowledge for you to know. Okay, with the thermistor, we can only achieve the measurement range, which is smaller than 100 degrees Celsius, right? And this is a very, very cheap solution for us to implement temperature control in industry, in society, or in the home environment, right? So normally in the factory environment, the temperature will never go beyond 100 degrees, except for the manufacturing process, okay? The ambient temperature inside the factory, ambient temperature inside the school, inside the hospital, inside the shopping mall should never exceed this value, all right? So otherwise, it's difficult for us to stay inside, all right? Okay, so this is a very cost-effective solution, all right? And this slide basically show you more example, okay? Or then you may want to know how to convert resistance of thermistor into output of the voltage. Then this is just a simple circuit. Okay, so from here you will see when temperature increase, resistance value reduce, then the output voltage will increase, okay? Because when this resistance reduce, then this one will move up, because this resistance is a constant, right? So you have a nice property, right? So graphically, we use this symbol to represent thermistor. You see, we put the T and raised to the power 0. And if this is NTC, we put the negative. If it is a PTC, we do not put the negative sign, okay? Negative means it's NTC, okay? And physically, you will see thermistor looks like this, right? So it's quite straightforward, okay? Then, if let's say our measurement range is larger than 100 degrees, then we must use RTD. So RTD means resistance temperature detector. So this is a kind of resistor, but you can consider is a customer-made resistor. Okay, so it's not the standard resistor. So basically, we warm a thin film on the base substrate on the cylinder. Okay, and wire worn on the cylinder or placed on the substrate, ceramic substrate. Okay, and we may also create the coin like this structure, right? And normally the material, temperature sensitive material are platinum, nickel, and the copper. All right, so it looks like a resistor. All right, okay, but however, its measurement range is much larger than thermistor, right? So, and the advantage of making use of RTD is to have a better accuracy, wider measurement range, all right? Okay, and also this is a very less expensive device compared to Warren expansion, infrared camera. Okay, so this is a low-cost solution for us to implement temperature sensor, right? So once we know how to convert temperature into resistance, then you may want to know how to convert resistance into DC voltage, all right? So there are plenty of solutions. So these are the two popular ones, okay? So we just use a series of two resistors in order to convert this variable resistance into variation in DC voltage, all right? Then this will be output to the microcontroller, all right? Another solution is use this famous Priest circuit, right? So you can use a thermistor in pair, okay? If you use in pair, then in this case, we can use the value of these two thermistor, okay, or RTD, okay? So in pair, then these two resistors will be the sensing element. Then for these two resistors will be R, okay, with no value, okay? So all in this Priest circuit, and this is RTD or thermistor, and the remaining three are the normal resistor. So it does not matter, all right? So then in this way, we can pick up the difference of voltage across these 2 points, the difference of voltage across these 2 points, all right? So this is a way to convert resistance into DC voltage. Then besides these two cost-effective principle for us to follow, of course, if you do not worry about the cost, you may have many other principles, such as making use of infrared camera, okay? Because every body with temperature, as long as it's not zero temperature, black hole is a zero temperature. This is why black hole never emit any electronic wave, right? So any body except black ball will have emit radiation, okay? Then we can use a camera to capture, okay, electromagnetic wave, and in particular, electromagnetic wave at the range around the infrared, okay, wave, right? Then we can have this thermal image. Then we know, okay, the bright area corresponds to higher temperature, dark area corresponds to lower temperature, right? And the black color does not mean zero. Try not to interpret it as zero. Actually, it's not a zero, okay? because there is a certain ambient temperature there, right? So you see the human body head has a higher temperature, the face, you see higher temperature, right? So it's very interesting. But of course, this is very expensive, right? Solution. Okay, you can also make use of different property in terms of linear expansion, volume expansion. Then we put the two method of a different property together. When they expose to the same temperature, because they will expand differently, this will create distortion. Then this distortion eventually give us indication about the change in the temperature, okay? Because this distortion can be converted into either voltage, resistance, or capacitance, all right? So there are many other principles for us to follow, all right? So then after the implementation of first step inside your sensor or measurement and the sensing system, always remember to do the second step, which is calibration. So calibration is to make sure that the output from the sensor is exactly equal to the value of the temperature on the measurement. In addition, we can assign the unit of the measurement to the output, which is equal to the unit of the measurement of the input. All right. Then here we should ignore the unit of a measurement of intermediate value after the sensing element. All right. So after calibration, and then your product or system is more or less ready. Then in this case, you must do extra work, which consists of doing error analysis. So then you use your new sensor to repeatedly take experimental data. Then in this way, you can calculate the mean value and the standard deviation, etc. You can also vary the input from small number all the way to a large number, then vary the input from a large number to a smaller number. Then in this case, to see whether the error in the first case is the same to the error in the second case. If there's no gap, so it means your sensor has no hysteresis error. Otherwise, there is a hysteresis error, right? And these data are needed by the user of your sensor or by the buyer of your sensor, right? Okay, so that's all about today's lecture. So the key takeaway from today's lecture is for you to know the basic physics behind temperature and also the basic equation behind the calculation of temperature. And secondly, we have studied some typical way for us to do indirect measurement with the temperature, right? And in particular, we have studied two popular and cost-effective solutions for us to follow in order to guide the design of a measurement and the sensing system for temperature. Thank you for your attention. I'm looking forward to seeing you in the study of the next lecture.